a tank. All right, so in fact, I'll request help from the crowd here to tell me what we got given here.
The head loss.
Head loss. We're given the head loss as, is it an equation? Okay, it's an equation, right? 4v squared over 2g, right?
Yeah.
Okay. All right, what else are we given?
The pump head.
Okay.
So the pressure head.
Oh, it gives us, head loss is a pump head, okay. 2q minus 4q squared, okay.
20.
Oh, it's 20?
Yeah, minus.
20 minus 4q squared, okay, which is typical, that it declines as the flow increases. And, okay, so that's, okay, good, good. So this is what we're given, we must be given this as well, right?
Yeah, 13 feet.
13 feet.
And then the pipe area.
Pipe area, right?
Yeah, 0.1 feet squared.
Okay. All right, this is, you're gonna need two equations. I think of them by their names, but we're going to use the energy equation to relate upstream to downstream conditions. It's going to include the head loss term, and it's going to include the head added by the pump. And so that's one equation, the energy equation. And I was thinking that we needed the pump, this pump power equation, but now I'm not so sure because it doesn't ask us for the power. It doesn't tell us anything about the power. So I think not. Let me give that to you. That's it in general. Flow rate, specific weight, the shaft, head added, and the efficiency. But we're not given any of that information. I think we're only going to use the energy equation. Now, we generally call this shaft, this book I think generally calls this a shaft head, but here they're calling it the head added by the pump, so I'll just say that. Okay, upstream total energy plus whatever the pump adds equals downstream total energy plus head losses. Take our datum at this location, so and this is 13 feet, that's 0. Say location 2 is here, so those are 0, that's 0. We do have to consider the velocity head at the downstream side, plug in those equations, and I think what would be worth doing is relating, substituting for flow and area here in this term. So we know that right, so then we square that, we get okay. And that's our head loss. And then we can substitute things in. So on the left-hand side, we got minus yeah, and so we should do the same thing here. That's so we cut just put it, I think that's why they did that. Okay, so now we've got a complicated equation for Q. Let's just see what we've got here. We've got 1 over 2GA squared. That's held in common between the two. And then we've got Q squared plus okay. So not so hard actually, because then we've got another 33 equals moving this over 4 plus 1 over 2GA squared times. Okay, and once you substitute in what A is, then you're just going to get some constant times Q squared over here. Oops, I messed that up. Q squared, because I put the Q out here. Right, so it's I combine these into 5Q squared. Pull that out there, put the 5, move that over. Okay, I think I did that right. Equals 33. And then you just solve for Q. forget what Q is. .67. Okay, yeah, that looks right. That looks right. Questions? Yeah, I'm going to change this back to okay. Let's go on to the next one then. Any questions from the people watching on Zoom? Basic idea is just use the energy equation, put everything in terms of Q, solve for Q. That's what I did. Noting that you can, yeah, you're given the upstream head, the downstream elevation head is 0. You do have to include the downstream velocity head, which is, that's what this is. All right. Let me skip around a little bit to the ones that I think are relatively easy. Wish I had my, let's see. I think number,
Do you want me to pull it up on mine?
maybe you could work on that while I. But then you'll have to be going back and forth from screen sharing and that. This one I think is relatively easy. Number 5.
Okay.
So you're saying that there's inflows to a basement. You're pumping the water out. It gives you some information about the basement area and the rate at which you want to lower the water depth. Gives you some information about the inflows and asks you to calculate the outflows. that's a problem that'll use the continuity equation. Remember we said there were 4 separate cases, whether or not it's incompressible fluid or not, and whether it's steady or not. This is unsteady, and it's water, it's a liquid, so it's incompressible. Problems with one of those cameras too,
I
wouldn't
think
focus.
one of them got water damage, so it goes out of focus constantly.
Oh, really? It did
Yeah.
get.
And then the top one that was,
Okay.
yeah, but it's fine. The zoom one is good.
Yeah, that one. Do you think it's? We'll have to switch it. I noticed Sarah has one more in the office, and I went and grabbed one from my computer this morning. That one got water damage.
I think both of them did. It just, one of them fared it better.
Okay.
Yeah.
And
This is the recording, this is the zoom one's
okay.
good. Yeah. Oh, okay,
Okay.
just got back in focus.
Bring the rice in.
Put in the desiccator upstairs.
Oh, do you have a desiccator up in the
In environmental lab?
environment?
But we put chemicals in there, so I don't know if.
Oh, okay. Yeah. Okay. This is our equation. The volume is going to, the surface area of the basement and the rate of change of the water depth is our dV/dt on the left-hand side. So that's the equation we use. I think the only other complication is that you might have to do a unit conversion at 7.48. You have that number in your head there, doing that 400 and something.
400.
48.
448 point. .8.
Mm-hmm.
Okay, so I'm not going to do any more on that one. Let's do one of the momentum ones. I think those are often troublesome. Let's look through the ones that seems like is the most troublesome. This one's one's number 7 it is, and then it uses both momentum equation and continuity. What's that?
You can take a picture with your phone and just have it at the
Yeah,
board.
that's true. Good, thank you.
Sure, sure.
Have it with me, yes. Rather than wandering around. You just had a strange noise here. Oops.
Is it visible?
Yeah. All right, yeah. All right, so we're given the two jets with a given velocity and the diameter of this circular jet, and then asked to find the here. The equations that we would use and actually we're going to have a Q1 from this jet and a Q1 from that jet. They have the same velocity and diameter. They come together, and that would be the velocity, the outgoing velocity. So I would probably start there. Calculate the flow.
.157.
Okay. 157.
That's what I.
They have a very complicated way of doing this stuff. Okay, so 0.157. set up the momentum equation for the one of the directions. Let's see if that works for us. So this is the sum of the forces acting on our control volume. We don't have any, okay, because there's no pressure. These are jets, and there's no external force, and there's no pressure forces. So that's 0. And we know that only one of these has an x velocity. So if we were looking at the x momentum, the only contribution is from this one. That would be, now we don't know V2, so that would be yeah, so we could use that, right. So I think the way that I would do this, is that we need the angle, and that there's two equations and two unknowns here. It's the velocity and the angle, and so you could do the x components and the y components, write them as a ratio, and then that's going to give you an equation for the angle. Because you're going to get I don't really want to go through all the math though, but the idea is that we can separately do the momentum equation for the x and the y. And then that will give us an equation for the sine of the angle and the cosine of the angle, where V2 is in this unknown direction, theta. Then once we have an equation, those two equations, and if we put them in a ratio, then that will give us, it'll have, that equation will look like something like cosine of the angle over sine of the angle equals an amount. And then you can use that to figure out what the angle is. And once you know the angle, then you can go back in to one of the equations and figure out what the velocity is. And then once you know what the velocity is, you can use your continuity equation to figure out what the diameter at location 2 is. So that's a pretty involved problem. Certainly more involved than I would do on a test.
I think someone had a question.
Sure.
Wouldn't you be able to do this, I guess, a little bit simpler by just doing it based off of the, even obviously with this one, because they're the same value, it's 45 degrees, and we can figure that out, but even if they weren't equal, couldn't you still kind of do it by using the velocities as lengths and just solving the triangle and finding finding the angles that way or finding the angle that way, just treating it as basically a giant triangle.
I think in effect you're doing the same thing, you're just doing it yeah, I think that is, you're just in effect doing the angles become the components of the right, I mean the distances become the sides of the right triangle. So yes, I think it is.
Okay, so that begs the question then, and this might be really simple. Once we have that angle, what equation are we using to find that velocity?
Okay, and I'd say that what you jump to is the idea that it is going to be 45 degrees. And so that makes some sense that if you look at the x and the y momentum, they're going to look identical because of the fact that these two velocities are the same and the diameters are well, the diameters don't really, yeah, the diameters matter too because then the momentum is the same. So that's what leads to the angle being 45 degrees. So let's just say that we could get to there by doing all of that. It's a little, it takes several steps because you write the x momentum and the y momentum, and you find you get, that leads to theta equals 45. Where do you go from there? I guess that's your question, right, William?
Yeah, where do you go from there? What kind of things do you do to find
Okay,
that?
so I think that's actually simpler, arithmetically more not so complicated. So let's just say that we did this, we got theta equals 45. What do we do with it? So what do we do with it then? Yeah, so yeah, because that doesn't give you any information actually, because all it's saying is that momentum in equals momentum out. Let's see. Oh, but I guess it does actually. So let's just look at the x component. So we have 0 equals, you want to give me this product here?
.3045.
Okay. And it's V2, the way I define it, cosine of theta minus 10. So then that gives us an equation to find V2. This is, it's just V2 is what's that, 0.707?
Mm-hmm.
Yeah. It's 14.14, right? Yeah? And so, and you could do the same thing. Okay, okay, and then once you do that, so we use the x momentum equation to give us the, and did the momentum in equals the momentum out. So there's no, in effect, there's no change in x momentum. And then once we have that, then we can say that and that has to equal that we had previously, and then you can use that to solve for the diameter of the jet. V2 is, oh, okay, F2. That's our Q in equals Q out. Yeah.
I got 0.029, but I can double check.
Oh, for D2?
Yeah, I can double check.
So wait, just a quick question, and because I'm actually doing the problem as we're doing it here. For the only things that they're actually asking for is the velocity and the angle.
Okay.
My velocity, my initial velocities V1 and V2 are 11. So my V final is just going to be 11 divided by 7.07, right?
Right. So yeah, this is, your version's probably got, or does have different values for the velocities and the diameters.
Okay, I'm still getting that wrong.
Okay.
So for example, if I do 11 divided by cosine of 45, I get 15.55, and they say that's wrong.
Okay.
Is that in radians or degrees?
Degrees.
Mary says she's having the same issues.
Yeah, and actually it does say it gives the velocity here as half of what I calculated. So what's the, so
So Jowey recommends 11 divided by 2 times cosine 45.
Yeah, doing it that way, dividing by or multiplying it by cosine over 2 will, or cosine 45 will get you the right answer.
yeah, I'm not getting their answer. I don't want to figure out where I messed up. but clearly I have somewhere, I don't see anything different. We did it a different way, so I'm having a little hard time of figuring out what's different about what I did from what they did. In my direction. Yeah, I'm sorry, William, I'll have to look more carefully at this one to see, either their answer's wrong or my answer's wrong. I don't see, yeah,
I think what it is that we have 2Q in equals Q out. So all we have to do is say that divide by 2 is what final answer is.
yeah, you're saying that maybe it was in this 2 that I messed up?
I think that's right, but
No,
it's not
you just-
account for that, it's only
yeah.
1 Q.
Oh, that's why it's different, yeah.
If you divide it by 2, your answer ends up being right.
Yeah,
Yeah.
right, correct, that is, their velocity is half of mine. And I don't see why you wouldn't have to, if you do a mass balance, all of that mass is coming, so I think that, yeah, I believe that I've done it correctly. Yeah, so it may be, William, that the answer's wrong. I will double check against the solutions here. Yeah, that's all I can say. It seems like maybe their answer's wrong. So, okay, were there other, I picked a good one, I guess. If there are more problems in particular that you have, I'm available again this afternoon during office hours, although I'll say